Hello, dear students. In this video, we will solve an exercise related to the study of real-valued functions, the intermediate value theorem, and solving equations by successive approximations. We consider the function f defined on the interval from 0 to positive infinity as f of x equals 9 times x plus the quantity 15 minus 2 times x, all multiplied by the square root of x. And the function g, also defined on the interval from 0 to positive infinity, is g of x equals 18 times the square root of x minus 6 times x plus 15. First, construct the complete variation table of the function g. Second, prove, without solving it, that the equation g of x equals 0 admits a unique solution on the interval from 0 to positive infinity. This solution is denoted alpha. Third, provide a 2-decimal place estimate for the value of alpha. Fourth, deduce the sign of g of x for every x in the interval from 0 to positive infinity. Fifth, prove that for every x in the interval, the derivative of f of x is equal to g of x divided by 2 times the square root of x. Sixth, use this to construct the complete variation table of the function f. The function named g is a sum of functions that are differentiable over the open interval from 0 to infinity. Therefore, the function g itself is differentiable on that same interval. Derivative of the function g. The derivative of the function g, denoted g prime of x, is first written as follows: 18 divided by 2 times the square root of x minus 6. This is because the derivative of the square root of x is equal to 1 divided by 2 times the square root of x. The derivative of 6 times x is 6, and the derivative of a constant is 0. This expression simplifies to 9 divided by the square root of x minus 6. Placing everything over a common denominator yields 9 minus 6 times the square root of x, all divided by the square root of x. Sign analysis of the derivative. The above expression, that is, the quotient of the numerator, 9 minus 6 times the square root of x by the square root of x, has the same sign as its numerator alone, namely 9 minus 6 times the square root of x, then 9/4, and negative when x is strictly greater than that value. We solve the inequality. 9 minus 6 times the square root of is strictly positive. This is equivalent to saying that 9 is strictly greater than 6 times the square root of x. By dividing both sides of the inequality by 6, we obtain 1/2 is strictly greater than the square root of x. Then, by squaring both members, we get 9/4 is strictly greater than x. Thus, the derivative, g prime of x, is positive when x is strictly less than 9/4, and negative when x is strictly greater than that value. Computing a few values, we have g of 0 is equal to 15. G of 9/4 is equal to 57 divided by 2. studying the behavior as x approaches infinity. We then express g of x in the following form. G of x is equal to x multiplied by the expression 18 divided by the square root of x minus plus 15 divided by x. This is because we factored x out of the original terms. Now, the limit of 1 divided by the square root of x as x tends toward infinity is equal to 0. Likewise, the limit of 15 divided by x as x tends toward infinity is also 0. Therefore, the sum 18 divided by the square root of x minus 6 plus 15 divided by x tends negative 6. As a result, the function g of x tends toward negative infinity when x tends toward infinity. Variation table. Based on all the preceding steps, we can construct the variation table. As x approaches 0, the value of g is equal to 15. At the point where x equals 9/4, the derivative is equal to 0, and g reaches a local maximum equal to 57 divided by 2. Then, g decreases steadily and tends toward negative infinity as x approaches infinity. Therefore, the sign of the derivative is positive before 9/4, 0 at that point, and negative beyond. As a result, the function g of x is increasing on the interval from 0 to 9/4 and decreasing on the interval from 9/4 to infinity. Initial statement. Let the function g be defined by g of x equals 18 times the square root of x minus 6 times x plus 15. The goal is to demonstrate, without explicitly solving, that the equation g of x equals 0 admits a unique solution on the interval from 0 to positive infinity. This solution is denoted by the Greek letter alpha. Study on the interval from 0 to 9/4. On the closed interval from 0 to 9/4, we observe that the function g is always greater than or equal to 15. If, for every x in a given interval, the function g of x remains strictly positive, or at least strictly greater than 0, then the equation g of x equals 0 cannot have any solution on that interval. Conclusion. The equation therefore has no solution on the interval from 0 to 9/4. Study on the open interval from 9/4 to positive infinity. The function g is continuous because it is differentiable, and it is strictly decreasing over the interval from 9/4 to positive infinity. Theoretical reminder. A continuous and strictly monotonic function, here strictly decreasing, is bijective over an interval. This means it takes each value exactly once, which implies the existence of a unique solution for any equation of the form g of x equals k, where k belongs to the image of the function, intermediate value theorem. Additionally, we have g of 9/4 equals 57 divided by 2. The g of x, as x tends toward positive infinity, is equal to negative infinity. This means that the function transitions from strictly positive values to strictly negative values. In other words, the image of g includes all real numbers strictly less than 57 divided by 2. Thus, 0 belongs to the image of G. Final conclusion. According to the bijection theorem, also known as a corollary of the intermediate value theorem, the equation g of x equals 0, therefore admits a unique solution within the interval from 9/4 to positive infinity. And since we have already ruled out the possibility of any solution on the previous interval, namely from 0 to 9/4, we can conclude that the equation g of x equals 0 admits a unique solution over the entire interval from 0 to positive infinity, which we denote by the Greek letter alpha. While waiting to continue the video, don't forget to subscribe, like, and share the video, as well as leave comments. Using a calculator to narrow down the solution to the equation g of x equals 0 to the nearest hundredth, this method relies on the table of values function integrated into most scientific calculators, often labeled table, TBL, or tab. Objective: we aim to approximate the value, called alpha, the solution to the equation g of x equals 0, with an accuracy to the nearest hundredth. Step 1. Access the table menu. On a scientific calculator, such as a Casio, for example, press the menu button. Select the table option, usually via a number key or arrow key, depending on the model. Theoretical reminder: the table menu allows you to quickly observe the values of the function for different x values. This helps you detect when the function changes sign, which is a strong indicator of the presence of a solution. Step 2. Entering the expression of the function g. We are working with the function g of x equals 18 times the square root of x minus 6 times x plus 15. You should enter this expression into your calculator as follows. Multiply 18 by the square root of x. Subtract 6 times x and add 15. Note, depending on your calculator's interface, the square root may be entered either as square root of x or as x raised to the power of 1/2. Step 3. Choosing the parameters for the table of values. This step involves configuring a value table to observe the behavior of a numerical function over a chosen interval. You will enter starting value, type 2.5, ending value, type 10. Step: the interval between two consecutive values of the variable, type 1. Theoretical reminder: when studying a function with spreadsheet software or a graphing calculator, it is common to choose an interval of numeric values for the variable, usually called x. The step determines how much x increases from one row to the next in the table. Selected parameters for the table: initial value for x, 2.5. Final value for x, 10. Step 1. Value table observations. Theoretical reminder. This table offers a graphical or numerical way to approximate how the function g behaves. From the entries, we can see that as x increases, the function decreases steadily, suggesting a downward trend. A complete study would require confirming this behavior using a derivative, but here, the table already gives a helpful intuition. By examining the resulting table, we observe that g of x does not equal 0 anywhere between 2.5 and 10, which means that the solution to the equation g of x equals 0 is not located within this interval. Pro tip: if too many rows are displayed at once on the screen, you can use the arrow keys to scroll through the full set of results. We continue by examining the values of x from 11 to 20, so we configure the value table as follows. Start. Enter a value such as 11. End. Enter, for instance, 20. Step 1. By observing the resulting table, we notice that g changes sign between x equals 13 and x equals 14. So we proceed to reevaluate the function between these two values. In this part, we reduce the step to 1/10 to narrow down the value of alpha to 1 decimal place. Since the sign change occurs between 13 and 14, we configure the table as follows. Start 13. End 14. Step 0.1. After analyzing the new table, we observe that g changes sign between 13.5 and 13.6. To further narrow down the value of alpha to the nearest hundredth, we study the interval from 13.5 to 13.6 with a step of 0.01. The configuration is as follows. Start 13.5, end 13.6, step 0.01. From this, we observe that g changes sign between 13.53 and 13.54. Step 4. The calculator will display the values of g of x line by line. Pay attention to when the function changes sign. If g of 13.53 is greater than 0, and g of 13.54 is less than 0, then we conclude that the value called alpha lies between 13.53 and 13.54. 4. Sign study of the function g. We are asked to determine the sign of g of x on the closed interval from 0 to positive infinity. From the sign table, we can observe that g of x is strictly positive before the real number alpha, equal to 0 at alpha, then strictly negative after alpha. This tells us that g changes sign exactly once and thus admits a single real root, which is possible because g of x is continuous, a requirement for applying the intermediate value theorem. Theoretical reminder: a continuous function that changes sign over an interval must have at least one root within that interval. by the intermediate value theorem. Now, regarding the function f, it is defined as the sum and product of functions that are differentiable over the open interval from 0 excluded to positive infinity. Therefore, this guarantees that f is itself differentiable on that same interval. Theoretical reminder: if a function is composed of sums, products, or compositions of differentiable functions, then the function itself is also differentiable, as long as each component function is differentiable over the interval in question. We are given the derivative of f of x is equal to the derivative of 9 times x plus the expression 15 minus 2 times x multiplied by the derivative of the square root of x plus the derivative of 15 minus 2 times x times the square root of x. Theoretical recap: the derivative of a sum is the sum of the derivatives. The derivative of a product u times v is u prime times v plus u prime v prime. The derivative of the square root of a function u of x is u prime divided by 2 times the square root of u. The derivative of the function f of x becomes 9 minus 2 times the square root of x plus 15 minus 2 times x, all multiplied by 1 divided by 2 times the square root of x. Here, we apply both the derivative rule for square roots and the distributive property. After placing all terms over a common denominator, this expression becomes 18 times the square root of x minus 4 times x plus 15 minus 2 times x, all divided by 2 times the square root of x. Simplifying further, we obtain 18 to the square root of x minus 6 times x plus 15, all divided by 2 times the square root of x. We then observe that this derivative is equal to g of x divided by 2 times the square root of x. We found that the derivative of the function f, denoted f prime of x, is equal to the following expression: the function g evaluated at x divided by 2 times the square root of x. Theoretical reminder: the derivative of a function represents the function's rate of change. Depending on its sign, a positive derivative means the function is increasing. A negative derivative means it's decreasing. And a zero derivative indicates a stationary point. Since the denominator, 2 times the square root of x, is always strictly positive for all strictly positive values of x, the sign of x depends only on the sign of g of x. We are also given f of 0 is equal to 0. The function f of x is defined as 9 times x plus the quantity 15 minus 2 times x, all multiplied by the square root of x. Expanding this expression gives f of x equals 9 times x plus 15 times the square root of x minus 2 times x multiplied by the square root of x. Factoring this expression using the common factor x times the square root of x, we get x times the square root of x multiplied by the sum of three terms, 9 divided by the square root of x, plus 15 divided by x minus 2. Theoretical reminder: factoring an expression means rewriting it as a product of factors, which is especially useful when studying signs and limits. As x approaches infinity, both 9 divided by the square root of x and 15 divided by x tend towards 0. Therefore, the limit of f of x as x approaches infinity is equal to -2 times positive infinity, which equals negative infinity. Theoretical note: the limit of a function as x approaches infinity reveals its long-term behavior. Here, the fact that f tends toward negative infinity indicates a strong downward trend past a certain threshold. Variation table of the function f. From all of this, we can now construct the complete variation table of the function f as follows. The first row corresponds to the function g. It is positive from 0 up to alpha q, equal to 0 at alpha, and negative beyond alpha. The second row corresponds to f prime. Since it depends on the sign of g, it follows the same pattern: positive, then 0, then negative. The third row represents the function f. It is increasing from 0 to alpha, reaches a maximum at alpha, then decreases and tends toward negative infinity. While waiting to continue the video, don't forget to subscribe, like, and share the video, as well as leave comments. Dear students, thank you for staying with me until the end of this video. Until the next one, take care and goodbye.